In one of our previous lecture, we have seen that the real line R in standard topology is not a compact space, but closed intervals of real line R are compact subspaces. So in this lecture, we will prove that closed intervals in R are compact. In addition of proving closed intervals are compact, we will also study two more type of compact spaces, limit point compact and sequentially compact spaces. Let's begin with proving closed intervals in R, or closed intervals of real lines are compact. So in order to prove this, we are going to use this theorem. So let me state a theorem without proof. And if you are interested in the proof of this theorem, you can take a look in Munker's book. So, but we are going to use this theorem to prove closed intervals in real lines are compact. And here is the statement of this theorem. Let X be a simply order set. Let X be a simply order set having the least upper bound property. Let X be a simply ordered set that has the least upper bound property. In the order topology, its closed interval in X is compact. So this theorem, it tells us that every closed interval in a simply ordered set that has least upper bound property it's compact. Now let me write down a corollary. So this corollary will tell us closed intervals in R are compact, and we will be using this theorem to prove the statement of this corollary. So here is the corollary. So this corollary, it says every closed interval in R is compact. This is one of the most important result in topology. So we are going to use this theorem to prove this corollary. So in order to prove this corollary, or in order to use this theorem to prove this corollary, now what we need this R is simply order set, and that has a least upper bound property. Obviously R has a least upper bound property, and we have seen in the lecture for order topology, in that lecture we have defined simply order relation, and also we have given the example of simply ordered set. So we have seen in that lecture R, if we consider strictly less than relation in R, then strictly less than relation is a simple order relation. So R with strictly less than relation is a simply ordered set. and also this R has least upper bound property. So by this theorem, we can say that every closed intervals in R is compact. Okay, just let me write down the things that I just described. R is a simply ordered set that has the least upper bound property. R is a simply ordered set that has the least upper bound property. So by the above theorem, we can say that every closed interval in R is compact. Okay, so we just proved that every closed interval in R is compact. Next, we're going to study limit point compact spaces. Let me first give the definition of limit point compactness, and then after that I will give some example of limit point compact spaces, and then after that we will see the relation between compactness and limit point compactness. So here is a formal definition of limit point compactness. Let's say a space X is said to be limit point compact. It's said to be limit point compact. Topological space X is said to be limit point compact if every infinite subset of X has a limit point. So this is the formal definition of limit point compact. A topological space X is said to be limit point compact if every infinite subset, here it says every infinite subset of X, every infinite subset in X must have a limit point in X, then the space X is called limit point compact. Now let me give you example of some limit point compact spaces, and also example of topological space which is not limit point compact. Okay, example number 1. Let's consider the set of real number R with standard or order topology, because standard and order topology on R, they are the same topology. So consider R with the standard topology. Then this R is not limit point compact. So we are saying that R is not limit point compact. So if R is not limit point compact, then R should have at least one infinite subset which it should have at least one infinite subset such that that subset has no limit point. Okay, and it is easy to find such a subset. For example, if you take this set of integer, which is the infinite subset of R, and obviously the set of integer has no limit point in R. If we are considering standard topology in R, then R is not a limit point compact, since the set of integers, which we denoted by this symbol, this is obviously infinite subset of R. The set of integer G has no limit point. So you have seen in one of our previous lecture why the set of integer has no limit point in R. Since we found infinite subset of R which has no limit point in R, thus the R with standard topology is not limit point compact. Let me give you example of a topological space which is compact. Let's consider X, which is the union of this singleton set 0 and the set of all the reciprocal of positive integer. Let's consider this union as a X, and which is obviously a subspace of R. Let's consider this is a subspace of R. Then the subspace, let me write down here the subspace X, which is the union of those two sets, is limit point compact. It's a limit point compact, and we have seen this in one of our previous lecture that the limit point of this set X is 0. So, and if you take any infinite subset of X, that infinite subset has a limit point 0. That's why this X is limit point compact. No matter which infinite subset you take of X here, that subset, those subset, the element of those subsets, they are going to be basically reciprocal of those natural number. So those subset, they're going to have 0 as a limit point. Thus, this space is limit point compact. Is limit point compact. Just let me write down the things that I just described. Is limit point compact since every infinite, because we need the limit of infinite subset, okay, is limit point compact since every infinite subset of X has 0 as limit point. Okay, those infinite subset of X, the element of the infinite subset of X, they are going to be the reciprocal of positive integer, and so if we take any such infinite subset, that subset has the limit point 0 in X. That's why this space X is limit point compact. Here is one more interesting example of limit point compact space. Let's consider Y is a 2-point set whose elements are Y1 and Y2. We have a space Y with 2-point set, and let's consider indiscrete topology. On Y. So we have this 2-point set with the indiscrete topology. Indiscrete topology means only the open set in Y are the empty set, and the whole set Y. That's the meaning of indiscrete topology. So if you consider the indiscrete topology, then that topology has only two elements, which are empty set and the whole set. Okay, now let's consider the another topological space, which is the set of positive integer, and let's consider this space with discrete topology. G plus with discrete topology. So discrete topology means uh, this is basically power set in G plus. So all those singletons are open in G. It is a power set in G plus. Okay. Let's consider this G plus with discrete topology. All right. Now let's take the Cartesian product of these two spaces. We are taking the Cartesian product of G plus with Y, and let's call that Cartesian product is X. Okay, so here basically if you want to say the graph or the picture of this X, so it's gonna be like this one. Let's say this is the set of integer, and this is our Y. And the elements of Y, these are like we have Y1 and Y2, and the integer, positive integer are on the horizontal line. Let's call them is 1, 2, 3, and then so on. So the element of X, they are like the order pair. You take the order pair of 1 with Y1, so that's gonna be 1 Y1, and you take the order pair of 1 with Y2, so that's gonna be 1 Y2. I think the first element is first coordinate in this order pair is 1, and similarly you take the order pair the Cartesian order pair of 2 with Y1, so that's gonna be 2 Y2, and then similarly the other one is here, which is 2Y2, and then you take the order pair of 3 with Y1, and then order pair of 3 with Y2. So there are more. So if you take the next one is 4, take the order pair, and so on. So these are the elements of X. I mean, these are not the only, there are more. In fact X is infinite set here. Okay, so let's consider this Cartesian product with product topology. With product topology. Product topology means every open set of this X, they are going to be in this form, U cross V, where U is open in X, it's open in X, and V is open in Y. It's open in Y. So that's the when we take product topology on this Cartesian product, so all the open set in X, they are in this form, U cross V, or the Cartesian product of U and B form, with U is open in X and B is open in Y. But the option for, or the choice for B, we have limited. B, it could be either empty set, and B, it could be Y, because V is open in Y and we are taking the indiscrete topology in Y. So there are only two options for V, which are empty set, or B is the whole set. If U cross V is non-empty, then there is only one option for B, which is Y. But there are like many options for U. In fact, infinitely many options for U, because U is an open set in G plus, and we are considering discrete topology. We have considered discrete topology on G plus. So all the one point or singleton in G plus, they are open set, and there are infinitely many open set in G plus. But for B, so if U cross B, or if this open set is non-empty, then there is only one option for B, which is Y. Okay, so now we are going to so X is a limit point compact space. Okay, so if X is a limit point, it's a product topology, then X is limit point compact. So why it is limit point compact? To so this space is a point compact. What you need to do is every infinite subset of X has to have a limit point in X. Okay, so to show that one, so we are just saying that X is a limit point compact, but we need to show this is actually limit point compact. So in order to show X is limit point compact, we need to show that every infinite subset of X has a limit point in X. So let's assume that A is an infinite subset of X. Now we need to show that A has a limit point. Okay, now here we have seen that all the elements of X, they are in this order pair form, with the first coordinate positive integer, second coordinate either y1 or y2. So if A is an infinite subset of X, then the elements of A, then A has elements of the form n is a positive integer and yi with I is 1 or 2, since all the elements of X, they are in this form. Okay, so here we want this infinite subset A of X has a limit point. So these are the elements of A. Now to show A has a limit point in X, since the element of X, they are in this form. N, Y, I. These are the elements of X. So let's say if this point, there are two options for I. It's gonna be 1 or 2, or if you want to, maybe we can write down ny1 or ny2. So n is a positive integer here. So the elements of the X, they are either in this form or in that form. Now let's say if this guy is a limit point of this infinite set X, then what we have to have here is any open set containing this point ny1 or containing this element ny1, ny1, any open set containing this element should intersect A at some point like this one, ny2. Okay, then we can say that ny1 is a limit point of A. That's the definition of limit point. If ny1 is a limit point of A, then every neighborhood or every open set containing ny1 should intersect A at some point other than ny1. So that means if this is a limit point of A, then any neighborhood containing this point or any open set containing this point ny1 should intersect A at some of this point ny2. And that is obvious, because let's say if you have an open set containing ny1, if we have an open set containing ny1, so that is going to be that open set, it is gonna be something like that, U cross B, because these are the open set in X if we are considering the product topology. Let's say U cross B is an open set or neighborhood of ny1, then for since U cross B is non-empty, so as I said before, if U cross B is non-empty, then the option for B is just Y. So this should be U cross Y. Okay, and there are two elements in Y, which are y1 and y2. So if this neighborhood contains ny1, so let's say U is like the singleton set n. This is open in G plus because we are considering the discrete topology. Let's say U is n singleton and then Y is like y1 and y2. So if you take the this Cartesian product, then the set is going to be n y1 and also n y2. Now from this computation you can see that if U cross B is an open set containing n y1, then it must also contain the other point n y2. Okay. Similarly, let's say if ny2 is a limit point of A, then the neighborhood containing or the open set containing ny2 should contain this point as well. That's why we can say that this ny1 is a limit point of A. So that means A has a limit point. If A has a limit point, then X is a limit point compact. Alright, so just let me write down the things that I just described. So any open set containing n y I also contains the point n y3 minus I. Okay, for example, if I is 1, then it's gonna be y2. If I is 2, then it's gonna be y1. Also contains the point n y3 minus I. So A has a limit point. Thus, since A is an arbitrary infinite subset of X, thus every infinite subset of every infinite subset of X has a limit point. That means therefore X is a limit point compact. Okay, this is another example of limit point compact, and this example is interesting. You will see in a few minutes why it is interesting. All right, now, so in this so far I gave you the definition of limit point compact, and then also I gave you some example of limit point compact spaces, and then also one example of topological space which is not limit point compact. And also we have done compact. We have studied compact spaces in our previous lectures. So one obvious question is, what is the relation between compactness and limit point compactness? So to find the relation, to explore the relation between compactness and limit point compactness, I'm going to give a theorem, and that theorem will give us the relation between compactness and limit point compactness. I'm not going to prove this theorem. If you are interested in proof, you can take a look in Munker's book. So here is the statement of this theorem. So this theorem will give us the relation between compactness and limit point compactness. And this theorem, it tells us that compactness implies limit point compactness. Implies the limit point compactness. Okay, that means if you have a compact space, then it is it is a limit point compact as well. So every compact space is limit point compact. And the question is the converse also true? That means if you have a limit point compact, is also the compact? And the answer is no. You will see in the next example here. So I'm gonna give you one example of a limit point compact space which is not compact. Remember, compact spaces are always limit point compact, but the converse is not true. That means if you have a limit point compact, is not necessarily it has to be compact. You can see in this example. Let's consider the space X, this Cartesian product of G plus positive integer with Y, the with Y with product topology, where Y is 2-point set with indiscrete topology and G plus with discrete topology. So we have already seen in one of our previous example, this set is, or this space X is limit point compact. So we have seen that. So let's say consider this X, then X is limit point compact, which we have already seen. But this space X is not going to be compact space. If it is not compact space, then what you have to, so what we need for a topological space not to be compact is we should be able to find at least one open covering. That open covering doesn't have the finite sub collection which covers X. And now we can find such a open covering for X that doesn't have the finite sub covering. So consider this collection of singleton. Since we are considering the product topology on this Cartesian product, so the open set in X, they are always in this form. U cross B, U is open set in G plus and B is open set in Y. So Y is open set, obviously this is open set, and the singletons where n is positive integer, those singletons are also open in G plus because we are considering discrete topology. So if you take the Cartesian product of singleton with Y, then this collection is gonna be open set. It is going to be the collection of open set in this product topology. Consider this, and obviously this collection is going to be a covering of X. If we take the union of those open set in X, their union is going to be X. So consider the open covering. Consider the open covering of X. Okay, so obviously this n is we have finitely many options for G plus, so that means n is a positive integer, so we have finitely many positive integer. So it is not possible to find finitely many set in this collection which covers X, because in X the first component is a finite set. If one of the component in Cartesian product is infinite set, then the Cartesian product is going to be infinite set. So since X is infinite set, But if we take only finitely many set from this open covering, then it is not possible to cover X. So that this open covering doesn't have a finite subcollection that covers X. Consider the open covering of X. Then this open covering has no finite subcollection that covers X. Okay, that means X is not compact. So hence X is not compact. But we have already mentioned that X is limit point compact. So we have an example of a limit point compact space which is not compact. So that the converse of this theorem is not true. That means if you have a limit point compact space, is not necessarily going to be compact. Alright, so now we're going to introduce one more type of compact space which is called sequentially compact. Then we're done with this lecture. So next we're going to introduce another type of compactness, or which is called the sequentially compact space. Okay, now let me give you formal definition of sequentially compact space, then I will give you couple of examples. So here is the definition of sequentially compact space. A topological space X is said to be sequentially compact. It's said to be sequentially compact if every sequence of points of X has a convergent subsequence. A topological space X is said to be sequentially compact if every sequence of points in X has a convergent subsequence. Okay, so if you form a sequence of points in X, and if that sequence has a convergent subsequence, then the space X is called topological space, because we are just taking the sequence as arbitrary sequence. So that means every sequence has the convergent subsequence. If the topological space satisfies that condition, then that topological space is called sequentially compact. Now let me give you example of sequentially compact space. So let X be a finite topological space. So we have a finite topological space X. If X is a finite topological space, then it is obviously going to be sequentially compact, because if we form the sequence of the point in X, since X is finite, then we can form the subsequence of that sequence which is going to be convergent. This is because X has only finitely many points. Thus every finite topological space is sequentially compact. Let X be a finite topological space, then X is necessarily sequentially compact. This is because X has only finitely many points. So if we take any sequence of the points in X, we can construct the subsequence which is convergent. Here's the another example. The real line or the set of real number R is not sequentially compact. If it is not sequentially compact, then R should have at least one sequence which doesn't have convergent subsequence. That means we should be able to find at least one sequence in R which does not have a convergent subsequence. Okay, so since we are saying R is not sequentially compact, that means we should find a sequence in R that doesn't have the convergent subsequence, and it is easy to find such a sequence in R. For example, you can take the set of positive integer or even set of integer. The real line R is not sequentially compact because the sequence of those positive integer 1, 2, 3, 4 up to this is the sequence of the point in R has no convergent subsequence. So we found a sequence which doesn't have the convergent subsequence. That's why R is not sequentially compact.